Right, so we'll be looking at a particle in a spherically symmetric potential with the wave function given by this right here. So x plus y plus 3z, and then this is multiplied by a radial part, which only depends on the radius. And we're going to ask whether this is an eigenfunction of the operator L squared. Alright, and I guess we can put a vector arrow on that. Alright, so, and then if it is an eigenvector of this, we're going to ask, what are the eigenvalues, what is the value of small l? And if it's not an eigenvector of this, then we'll ask ourselves, well, what are the possible values of lowercase l that we can measure, right? And this is actually a really fairly straightforward problem. If we basically put these in terms of the spherical harmonics. So what we're going to do first of all, we'll just put a question mark here because that's what we're going to be asking ourselves. Alright, so first we're going to put this into spherical coordinates. Alright, so we have an r sine of theta cosine of phi, so this is x, alright, plus y, which is r sine of theta sine of phi, or phi, I go to theta, okay, sine of phi. And then z, except we have this 3 here, so 3r cosine of theta, like this, alright? And it's multiplied by this radial part. Except now what I'm going to do is factor out this r, that since r only depends on r, we'll factor it out and stick it with the radial part here. So I'll just write that out here in the front. Okay, so this is like a new radial part, right? It's just our old radial part with an extra factor of r here. Sine of theta cosine of phi plus sine of theta sine of phi plus 3 cosine of theta. Okay, so since we're looking at the operator big L squared here, and the eigenfunctions of this are the spherical harmonics, we will now express the angular part in terms of spherical harmonics. So I went ahead and wrote out the first few of them, and it looks like basically we're only going to have to work with these because once you get into higher powers of L, like L equals 2 and 3 and on down the list, you start getting all these squared terms and terms with 2 trigonometric functions at once and all this other stuff. So we're going to just see if we can make this angular piece out of only these first few spherical harmonics. Alright, so this is all written in terms of sines and cosines and things like that. So let's just try to get those, just each sine and cosine and whatever in terms of spherical harmonics. So I'm going to go ahead and write this in a bit of a shortcut, just to get rid of these factors so we don't have to write them every time. So I'm just going to write y11 equals, we'll just call it minus alpha sine of theta eti phi. y1 minus 1 equals, this is a plus alpha sine minus I phi, and y1, 0. I'm going to call this beta here. Just splitting up the constants so that they're easier to deal with. All right. Okay, so well, this one here is easy. So we know when we find maybe we can write these out separately on a piece of paper. So cosine of theta is easy, because that only involves this one. It's just the y10 over beta, okay? All right, but now let's, what should we do? We should try to deal with sine of theta. So we want to get sine of theta out on its own, and also we want to make a sine and a cosine of phi, because our original, so like here we have a cosine of phi, and here we have a sine of phi. But notice that they're both multiplied by sine of theta here, and we have that factor right in here. So maybe we can keep this here. All right, so we remember that sine of phi is equal to e to the I phi minus e to the minus I phi over 2I, and cosine of phi is equal to e to the I phi plus e to the minus I phi over 2. Okay, so this is how we're going to get our sine and cosine of phi from this. All right. All right, so we're going to take a look at what happens when we add y11 and y1 minus 1. Okay, so these two. All right. What we get, well, there's an a sine of phi that can come out, and there's and you know what, I'm going to bring out an extra minus sign right here, okay? So that way this one is positive, we have an e to the I phi, and this one's negative, minus e to the minus I phi. Alright, well, looky here, this looks just like the top, the numerator or whatever of this sine of phi right up here. So all we have to do is divide by 2I, and we will have a sine of phi. So I'll write this on a new line. So I'm going to multiply by 2I. So here's that minus up here. So a 2I alpha sine of theta. So we multiply by 2I. Now we'll divide by 2I, except once we divide by 2I, this piece right here is going to be equal to sine of phi. So I'm just going to write sine of phi. Okay? All right. Now we're going to look at a y1 minus 1 minus y1, 1. Why did I pick that? Because I want this minus sign to go away, because I know what I'm shooting for. I'm shooting for the cosine of phi here, where these are both added together. All right, so this minus sign throws off my groove, so I'm going to put a minus right here to get this to a plus. All right, so we again will factor out an alpha sine of theta, and now with the minus sign trick and whatever, we have an e to the I phi plus e to the minus I phi. All right, same thing again. Once we and in this case we're not dividing by 2I, we're just dividing by 2. So we're going to divide by 2 and multiply by 2, and that will let us replace this term. Well, I'll just write this one in. We have a little bit more space. All right. So we'll replace this term right here with a cosine of phi. So a 2 alpha sine theta cosine of phi. Okay. So these are looking good. Where's our other paper? We had the first one that we did, right, was this. And this problem's a little bit contrived because these factors work out just nicely. So we don't have to have some really, really complicated summation of a bunch of spherical harmonics or whatever. But all right, so now what we're going to do is we'll just look at these parts over here. And again, because the problem is the way it is, I'm just going to keep these terms together, because if we go back and look at our problem, here the terms appear together. So here we go. Let's start with the top one right here. So we have a sine of theta, sine of phi, okay, right here. So that's this right here, okay, and that is equal to, in terms of the spherical harmonics, we're going to divide by, I'll just leave it, yeah, so we'll just minus 2i alpha. Alright, and you can bring the I upstairs and take away the minus sign. But alright, so minus that multiplied by what we had over here, y11 plus y1 minus 1. Okay, now we will do the same thing with our second piece down here. Sine of theta cosine of phi. Okay, this time there's a factor of 1 over 2 alpha in front. No I. And now we put in our spherical harmonics, which was y1 minus 1 minus y1 1 right here. All right, we are now ready to express our original wave function here in terms of the spherical harmonics. So here's that radial part that we're not worrying about, since we're just measuring the angular momentum. And now we start plugging in what we have here. Okay, lots of paper shuffling. Okay, so first we need a sine of theta cosine of phi. Well, that's this term right here. So 1 over 2 alpha y1 minus 1 minus y1 1. Okay, now we are going to plug in this part here, sine of theta sine of phi right here, and here's a minus sign, but we're just going to bring the I up to the top and take away the minus sign. Okay, basically multiply top and bottom by I. Right, so we have a plus I over 2 alpha, and I'm going to go ahead and write this down here. So y11 plus a y1 minus 1. So here's the closed parentheses, here's the open parentheses. Okay, kind of messy. And then our final term, we had 3 multiplied by the cosine of inverse cosine of theta, but we have a 3 over beta multiplied by y1, 0. So this is our wave function in terms of the spherical harmonics. All right. Let's see if we can make it a little prettier. And we're going to do that by combining these. So we just get a coefficient for each of these spherical harmonics. So let's go ahead and do y11 first. Okay. So with y11 we have a minus. So here's y11 up here. There's a minus sign. Minus 1 over 2 alpha plus I over 2 alpha ay11. Okay. Plus, similarly, we get the same thing except without this minus sign. 1 over 2 alpha plus I over 2. I wrote it in here. It's an alpha. 2 alpha. y1 minus 1. And our last one, still just a 3 beta, y1, 0. All right. Okay. So, by the way, what do we get when we act with the L squared operator on this? Well, the eigenvalues for that, so our little l, it only will only be looking at the radial part, and L is the bottom number on this. And look, they're all 1. So the only L we can get is equal to 1. So even though we have a few different sort of eigenfunctions of L squared, they all have the same eigenvalue. So it's degenerate, right? We have a mixture of these different eigenfunctions, but they all have the same eigenvalue of L equals 1. So measuring this state every single time, we'll come up with an L equals 1. And so our answer for this angular momentum squared part is the L times L plus 1 times h bar squared, which is equal to, since L is equal to 1, this is 2 h bar squared. All right, so now what we're going to do is we're going to look at the probabilities for getting the different m's. So the m is this number up on the top. And we haven't worried too much about normalization and different things, but we'll just kind of do that when we get to it. So I'll write this as probability of m equals 1, okay? And that is equal to this coefficient right here squared, or norm squared, or whatever, with the complex conjugate multiplied by the coefficient itself. So that is equal to, I'll write minus 1 over 2 alpha. You know what? Let's just factor this part out. All right, but there's a squared on it. So now we have a 1. I factored out a minus sign, so we have a 1 minus I, and then a 1 plus I. All right, we had one of these is like the conjugate of the other. So this is our coefficient, the norm squared of it. So what do we have here? We have a 2, right? So the i's will go away, the inner term. We have a 1 plus minus I multiplied by I is 1. So we have a 2. So we get a 2, and then this minus sign is going to go away because we're squaring it. we'll have a 1 on top, and then on the bottom we have a 4 alpha squared. Okay? And we'll plug in alpha in a bit. What's the probability of getting an m equals -1? Well, we go and we look at our coefficient. Here's the -1, Lm. So we look at this coefficient, norm squared, and we're going to factor out a 1/2 alpha again. Alright, and then what's left over is a 1 plus I, and then multiplied by its conjugate, 1 minus I. And this term, this product right here is the same as this one up here. And this one's the same as this one because the minus sign goes away. So this one is also equal to, I'm going to go ahead and call this 1/2 alpha squared. So this one's also equal to 1/2 alpha squared. Alright. So what's the probability of getting an m equals 0? Well, we look at our coefficient here, and we're just going to square this is equal to 9 on top and beta squared on the bottom. So here are our 3 probabilities, but we're going to have to normalize them in order to find kind of the relative probabilities, right? They have to sum to 1. But first we need to go and find what we had for alpha and beta. So if we look way back at our list of the spherical harmonics, this was alpha, this 3/8 pi to the 1/2 power, and this was beta, 3/4 pi. Alright, so I'm going to go ahead and copy these ones onto this sheet real quick. So probability of m equals 1 or -1, because they're the same probability, right? Equals 1/2 alpha squared. Alright, these are the same. So, alright, so let's put in some real numbers instead of alpha and beta. So because beta is equal to 3/4 pi to the 1/2, once we square it, we'll just get rid of that. And 9 over beta squared is equal to, so we'll have the 9 on top, and then we're going to flip the 4 pi up to the top, and on the bottom we'll have a 3. Okay, so what we end up with is this divides out with this to get a 3 on top. 3 times 4 is equal to 12 pi. And again, this is a relative probability. We'll have to sum them all to 1 in order to, anyway, basically we have to normalize it. And then these ones here are equal to 1/2 alpha squared. Okay, so here we have a 1/2, and then alpha squared, once we square the square root of 3/8 pi, we just get 3/8 pi. It's on the bottom, so we're going to flip it. So we have an 8 pi on the top and a 3 on the bottom, and we get an 8/6 pi equals a 4/3 pi. Alright, so here's our 2 probabilities. We have 2 of this one for m equals 1 and -1, and we have a much larger number, 12 pi, for m equals 0. So we are going to sum these up and then divide each of these terms by the sum to get the probability of each with respect to the others. So if I multiply Well, so let's just call this, if we put this in terms of thirds, we're going to multiply this by 3 on the top and on the bottom, so a 36 pi over 3, all right? And now they're all in terms of like pi over 3. So, last page, here we go. 36 pi over 3 plus 4 pi over 3 plus, all right, remember there are two terms of this, one for L equals 1, M equals 1, and one for M equals minus 1. Never mind, let's go ahead and simplify. So this is a 44 pi over 3. All right, so here we go. We have our final answer. The probability of M equals 0 is equal to, it was 36 pi over 3. And we're going to divide by this sum. So flip it upside down, we have a 3 over 44 pi. Right, the 3's will divide out, the pi's will divide out. Let's see, we have a 9 over 11 if we divide by 4. Okay, and then we'll go ahead and just look at one of these for now. M equals, say, minus 1, doesn't matter, they're the same. And this was a 4 pi thirds, right? Again, divide by the sum of all of them. So we get a 3 over 44 pi. All right, 3 is going to divide out, pi is going to divide out. Divide by 4, we get a 1 over 11. So 1 over 11, and we know that the probability for M equals positive 1 is the same as that for M equals minus 1. They had the same answer when we squared those coefficients. So this is also equal to 1 over 11. All right, and this sums, all right, so when we take the sum of all of these, they should sum to 1, right? 9 plus 1 is 10, plus 1 is 11. 11 over 11 is 1. All right, so that's the end of this little adventure.